aren't doing what they're supposed to be doing. Anyway, so we were going through these rules, and I forgot to start the tape, but that's okay. We talked about this on Tuesday, Monday, and then the last one, the zero exponent rule. A to the 0 equals 1. Anything does. Where this comes from is the subtraction rule again. A to the third over A to the third. Everyone knows that that's 1. It's something divided by itself. But if you did the subtraction rule, you do A to the 3 minus 3, which is A to the 0. So again, I'm just proving that the 0 exponent rule comes from the quotient of powers rule when you have a special scenario like that. So hopefully that makes sense and makes those easier to deal with. Okay, so what are we going to be doing today? Dealing with a whole bunch of different radical expressions. We're going to be doing a whole bunch of different operations with radicals, and we got to know what it means for it to be reduced. So that's the second line there. No roots are left to extract. So let's look at this real quick, this sentence. What does it mean to be reduced? No roots are left to extract. This is an example of not reduced. See, the fourth root of x to the fifth, there's enough x's in there to pull another x out. And we better understand that pretty quick when we're dealing with radicals here and different indexes. So making sure that occurs. And then there's a rule that you can never have a radical in the denominator. So we got to make sure we do something about that. And that's probably going to be the most complicated thing we have to deal with today. So looking at this, yeah, this is not simplified. You got to do something about that radical in the denominator. It's a skill that can be important in certain things that have to be done in calculus. All right, these are reduced. The fourth root of x to the third. Oh, there's just not enough x's to pull out of a fourth root. So that is done. And then notice there's no radical in that denominator. So so the one on the left for sure is good to go as far as reduced is concerned. Okay, so I'll leave that up there for a second for those that actually take notes, which should be everyone. But, you know, if you don't take notes and you get an A triple plus, fine. There's not anyone in that condition, by the way. So we all should be taking notes. Okay, so we can do that. All right, and then going to slide this down a little bit. Check that off. Just kind of hit no attendance things. Okay, and then we're going to toggle back and forth on properties of radicals. I'm going to be going back and forth liberally about if I have a square root of a whole bunch of stuff, I'm going to break it down into two separate radicals so I can, work with it and simplify it. Same thing with quotients. I may jump back and forth on that. I know Mrs. Fasola really enjoys teaching this through making the radicals fractional exponents and then using exponent rules. I may show one example like that as well. But look at what happens. X, y raised to the half. Well, x to the half, y to the half, kind of busting it out into two separate situations there. Is how she would actually attack this. So I'm going to be very liberal about that, and I'll show you as I go around asking you questions. Ethan, you're lucky. You're first. Lucky you. So go ahead and turn on that microphone. How you doing on this fine morning, Ethan? Oh, Ethan, Bocat Cat. How do you say your last name, Ethan? Oh, I did it. Okay. Yeah, we're going alphabetic. So, okay. Here's your first one, and I'll slow you. I'll direct the questions so that you know exactly what we're going to be doing here. And I'm probably going to do this just one way. Maybe when I get a later one, I'll show you what Mrs. Fasola does. Okay, so rewrite using properties of exponents and radicals. Cube root. Okay, so what do you know about 54 there, Ethan? What is 54? Okay, and then what's left over? Okay, is that good, by the way? Do you know about cube roots? Reverse that. The cube root of 27 is 3. There you go. Yes. So you just said that in reverse. And that's really where I hope all of you become. So when we're talking about cubed roots, perfect cubes, we should know these. You know, perfect cube of 1 is 1, perfect cube of 8 is 2, perfect cube of the next one's 27. 3 cubed is 27, 4 cubed is 64. And at least should know 5 cubed is 125. We should know these perfect cubes so we can stop here and rewrite this in our head like this. You know, oh boy, I've been having this happen all day long. What's going on? Where's my pen? Just stops writing. Okay. Cube root of 27 times the cube root of 2. All right. What about y squared? Is that good enough? Ethan, yes or no to be broken out? Ooh, no, it can't because the cube root, I need something times itself. How many times? 3 times. Y squared is just y times y. So this is stuck in jail, which many people feel like that when they're in school. All right, what's the cube root of 27 again, Ethan? And then everything else is stuck in jail. So cube root of 2y squared. This is what I mean about liberally going back and forth between busting it into separate radicals and then bringing it back into one radical. Okay, this is the way this goes, and this is how it works. Okay, I show you what Mrs. Fasola does. She changes 27 into 3 to the third. So then she rewrites this all like this. 3 to the third is 27, and then she raises it to the 1/3 power. And then she takes that 2 and raises it to the 1/3 power because that's what a cube root is, and then takes the y squared and raises it to the 1/3 power. And knowing that 27 is 3 to the third, 3 times 1/3 is 3 to the first. So she frees that in that manner. But then she says to herself, okay, this is not good. So this is stuck in a cube root, and this is stuck in a cube root. I don't know if I necessarily like that, but I do like the exponent idea of multiplying those and getting 3 to the first freed out of the radical. So just something to share with you. I will never write that again. I'm going to keep going with like trying to identify perfect things. Matt, we know about 81. Well, what's 81? What times what? It's a perfect square. Let's make this easier. Okay, and then what do you know about 9? Okay, so what is the fourth root of 81 then, based off of this breakdown that you did? Because actually, numbers are going to be the hardest to deal with. What is the fourth root of 81? Okay, so I'm going to write that as I know this is a perfect fourth root. I'm going to free that. What about 8 to the eighth? Do you remember what happens with that? You know, this is actually our Monday lesson. You're right. So I'm going to write that as, hey, this is going to be a perfect situation. And those that I got to talk to Tuesday, because I was back on at school Tuesday teaching a lesson. We talked about this. You know, this is a perfect situation. What do you do with the 8 and the 4, actually, Matt, in order to simplify that? Yeah, you divide. I actually might have said that in the Monday video as well. If you actually figure out that this is perfect, or like the Fasola method, this is a to the eighth, and then it's to the 1/4 power, and then 8 times 1/4 is 2. So that's another thing that works out well. Oh boy, Matt, you got a phone call. All right, and then 3. So again, I guess I'm writing that as it is. Okay, then real quick, Matt, during that phone call, what about b to the fifth? How am I going to break that down? I'm going to break that down into two different things here. So what am I going to break down b to the fifth to be? You are correct. You are correct. You are correct. Okay. And then what I like doing is this perfect fourth root, perfect fourth root, perfect fourth root. These come out. And I'm going to go ahead and erase this. Get this out of the way. What was the fourth root of 81 again? And then fourth root of a to the eighth. Fourth root of b to the fourth. And then stuck in jail, fourth root of b. Now I think I know why Mrs. Fasola did say something about b here, but what was the rule when we fourth root and we have an e odd power resulting on that b? What am I supposed to put around that? Do you remember, Matthew? Yeah, right. It's called the absolute value. Now, I think why Mrs. Vasola didn't is because B could not be negative if we're going to fourth root it still, because there's a leftover part on the inside. I don't want to scramble your brain with that. I want you to know that if a even index and you get an odd power, you should ensure that that B should be positive, and just leave it at that. Okay, so we do want to put an absolute value around that at the end. All right, Gracie. Ooh, good one, good one, good one. Now, Gracie, I'm going to tell you right now, the numbers are the worst. They are. So, what are we going to do about 128? What are we going to break that down? Starting off. Yep. 64. This is why this is a pain. I have to keep going. Yeah, that makes it better. And then what's each eighth? 222? 222. This is why numbers are the worst. How many twos do you have total? Do you count that? There's actually one more, right? That one. So I have 7 twos. So, okay. So it's 2 to the seventh. I think I'm going to do this way. We're going to break this down into the fifth root of 2 to the fifth. And then what's left over? The fifth root of 2 to the what? You're right. And I'm glad you had like kind of a questioning voice, but you were right. So that solidifies your questioning this idea here. I think we really should do that as opposed to any other way. I think in the other class, I wrote out all 7 twos, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. And then I did this, which is okay. But imagine if there was like more. Oh, then it'd be a pain. And then I highlighted this many because that's a perfect situation for a fifth root. Well, I think this handles the same thing, just understanding this exponentially. And then it's a little bit better and more efficient, I guess. Hey, how do I break down the x to the sixth? We're going to make it two different fifth roots. Not third, we have a fifth root. So I need x to the fifth. And then what does that leave left over? Well, 5 plus what equals 6? 1. Okay, so what we're doing is we're getting perfect fifth roots identified. And then how about y to the 10th? Is it perfect or not? Oh, it is. What is the fifth root of y to the 10th? Remember what Matt said about dividing? Because that really tells you what perfectly happens. So what's the fifth root of y to the 10th? Well, it's y. Say it correctly. Y squared. There you go. So fifth root of 2 to the fifth is 2. The fifth root of x to the fifth is x. The fifth root of y to the 10th is y squared. And that's how we want to break this down. That's why I liberally write these as different and separate radicals, trying to get the perfect ones out and then seeing what's left over on the inside. Fifth root of, hey, what's 2 squared, Gracie? and then x. Okay, so these are stuck in jail. And then we go ahead and clean it up. So 2 squared is actually 4. Okay, and then that is the final answer. No radicals needed because it's a fifth root. We don't have to worry about it. We're good with that. Okay, good. Ryan, USA. Okay, so Ryan, now you have the hard one, the very first radical with a fraction. So remember, the rule is no radicals in denominator. No rad in denominator. That's the rule. Maybe a brand new rule for you today. That's just it. And I'm going to tell you, this is what you do on this. You look, can you root it? Can it be square rooted? And if so, we're going to go ahead and do it. And or can we reduce the fraction? Sometimes reducing the fraction takes care of something that's in the denominator, a radical that's in the denominator. Because right now we have this in a radical in the denominator. It goes all the way down to the bottom. And then the worst thing that we have to do at the end is rationalize it. If we cannot do the previous two things, we are going to have to do a rationalize. And that is the worst. Okay. All right. So who are we on here? Ryan? Ryan, can we reduce anything in this fractional radical? Who? You're right. So let's not say the 125. What about the x? How can we reduce it, or what can happen to this x? Well, let me look up here. This is what I mean about reducing. What can happen there? Well, I don't know what that means because we don't have an equal sign. Okay, but I have an x to the fourth on the top and an x on the bottom. What should be able to happen? Okay, Ryan, we're going to have to remember this. Those cancel. When you have x to the fourth over x, what does that cancel to become? What's up on the numerator? Good. And then on the bottom, we notice we just have 125 now. So we've taken care of at least one component that used to be in the denominator as far as a radical is concerned. So this is the reducing part. If we can reduce and it does help us, we should. All right, next thing. We're going to start writing this as separate radicals. What's the cube root of x to the third, Ryan? Good. Does the cube root of y squared happen? Yes or no? What's the cube root of 125? What times what times what equals 125? And I actually list that as some of our perfect cubes that we should be aware of up here in the notes. So what times what equals 125? 5. So the cube root of 125 is 5. And then you reduced and then you rooted and you got a fraction that no longer has a radical in the denominator. So you are done. And that's what we need to understand about fractional radicals. Okay, try these 3 things. You can turn off your mic now. It sounds like you got some drums going on in the background or something. I'm not sure what that is. All right, so root it and reduce it. Actually, we reduced first with the x's and then we rooted and it ended up working out perfect. So we're good to go. Oh yeah, numbers are the worst. Okay, so here we go, Hannah. What do you know about 16? All right, and then what do you know about 8? So ultimately, I want you to write, what is 16? How many 2's multiplied together? Oh, that's too many. Oh no. Okay, so 2 times 2 is what? Okay. So how many 2's should I write for 16? There you go. Then how many 2's for 8? What time? How many twos are multiplied together for 8? Okay, so I have a total of, and I don't know if you want to do this. This is why numbers are the biggest hassle. But the fifth root of 16, not good enough. 16 is 2 times 2 times 2 times 2. It's only 4 twos. But then when I write this as one big radical and add the 3 twos from 8, now I have this. And now I can take that 2. That is 5 twos multiplied together. What's the fifth root of 5 twos multiplied together, Hannah? Mm-hmm. And then stuck in jail, fifth root of, which is just what's 2 squared. Yeah, so you want to rewrite it as that instead of like 2 times 2 or 2 squared. So we just determine who's stuck in jail. Numbers are a pain. They really are. So it is a little bit different situation there. Okay, I'm not sure how many we have of this. I think this is from Mrs. Fasola's old notes. I don't know if they have questions where the radicals don't really line up. You see that, David? See how this is a sixth root and a cube root? David? Yeah, so we got a problem. We can't just write this as one radical because they don't have the same index. Oh, David, what'd you do there? You're making me deaf here. Okay. All right. So so in this case, I think what we're going to need to do, first of all, what's 8? 8 is 2 to what power? You are correct. So I'm going to write this like this. And I'm going to do what Fasola does all the time. She just writes these as fractional exponents. When you have radicals with different indexes, you're going to want to do this. It's the only way that we can kind of get these to be alike. We can do something mathematically. But the other reason I did this is, something actually happens. I can distribute this power. This is a power raised to a power rule. And then, David, what's 3 times 1/6? Because that's what happened. There you go. And I'm going to make this 1/2 power now. What that did is that kind of knocked it down and reduced it a little bit. And then this is x to the 1/6. And then this is 2 to the 1/3. And this is x to the 1/3. And then what I'm going to do is I'm going to bring these two together. I'm going to use this as the commutative property. I can write these together as a product, and I can write these together as a product. I can switch the products around. Commutative. Hey, David, what am I supposed to do with these exponents? Which means you are doing what operation? You are correct. Just you were adding. That was awesome. Yeah, that's all I was looking for. So multiply by 3, multiply by 2. This becomes 2 to the what power? Oh, it's 3 plus 2, which is 5/6. And then don't you have the same thing with this one? Times 2 times 2. And then this is x to the 1 plus 2, which is 3/6 power. Now I know that reduces, but this is where I'm going to blow your mind. This could be written as a radical, and I'm not going to reduce this because I want to put these underneath the same radical. And the reason these don't come out is it's a sixth root. So there's not enough of each one of them to pull anything out. That's a bugger. Those are really a pain when they don't have the same index. It kind of leads to ugly questions like that. So we kind of use the fractional exponent rules to kind of break that one down, and nothing actually ended up coming out. So that one kind of stunk. Okay, so thanks, Dave. Genevieve, you're next. Oh no, Genevieve, you got a toughie. Now, Genevieve, remember what I said when you have fractional stuff, root it or reduce it. Does anything root right now? Is there any perfect cubes? Nope. Does anything even reduce? 2 over 9, n over m. Oh, no. So then you're stuck with that nasty rationalize. And what does that mean? Well, the rule is you cannot have a variable in a radical in the denominator. You can't have a radical in the denominator. So we're going to break this down. 9 is, I'll write this like this. So the numerator is the cube root of 2n. And then 9 is 3 times 3. So break this down and then m. And then you're going to multiply this by a fraction. And this fraction is going to equal 1. So whatever I do on top and bottom has to be exact same. Okay. So I'm going to give you another hint. It's going to be a cube root that you're going to multiply both top and bottom by. But let's just focus on the bottom. How many 3's would you like to have in a cube root, Genevieve? How many 3's would be perfect? 3. How many are you missing? Make your fantasies come true and add a 3 to the bottom. Okay, how many m's do you want? How many m's should you have in a cube root? 2 more. But it's got to be on the top as well because of what I put off to the side that I'm going to erase now. You need to multiply this fraction by a form of 1, and therefore it will not change its value, but it will change the way it looks. That's the only thing that will occur. Okay, so now look at what you accomplished. Down on the bottom, you got the cube root of 3 times 3 times 3, m times m times m. And the final answer will be 3m on the bottom. Freedom. You made that happen. Up in the numerator, 2 times 3, not a perfect cube, so we got a 6. N, no other n's. M and M, M&M's. Halloween, nothing comes out. So I should write the m's first. I guess I should be alphabetical. That is the accomplishment of simplifying that question, Genevieve, believe it or not. Because what did you accomplish? The only thing you did was you got rid of radicals in the denominator. And mathematicians demand that. I don't know why, but there are some reasons that are actual practical. But that's what you have to accomplish, and you did it. So really think about a cube root. We have a tougher one coming later where there's a fourth root coming up. Ooh, I see. Or actually a fifth root. Nice. Did I do this one in the other hour? Yeah, I think I did. No, I think I skipped it. Yeah, we'll go ahead and do it. Jad, real fast. Fourth root of 27. Is that perfect? Yes or no? No, but what's 27 times 3? I'm starting it for you. Can you see this screen? 81. Do you know what the fourth root of 81 is? It is. X squared times x cubed. Does anything break out of that one? Final answer. You got lucky. You got actually an easy one. Okay, so I'm a liar. This is why I skipped this one. What did I do wrong here, Jad? I didn't look at this. Does that say a fourth root here? Yes or no? Good. I'm glad I did this. Erase all of that, everybody. We did that completely wrong. Wrong, wrong, wrong. Okay. Sorry about that, everybody. So here's what we had to do. This is 3 to the third. So this is 3 to the 3/4. This is x to the 2/4, which is x to the 1/2. This is 3 to the 1/2. And then this is x to the 1/2. 1 divided by 2. All right. And then that's the only way that we can deal with when we don't have the same Indexes. So I completely misread that. My bad, dogs. So something completely different happens here. Okay, so Jad, what do I do with these exponents? Interesting, right? You don't multiply them. What do you do with these? You add them. So I need a and that's 2 times 2 is 4. So this becomes 3 to the 3 plus 2, 5/4. And then what does x to the 1/2 times x to the 1/2 become? Yes. Yes. Okay. Now, 3 to the 5/4. You better know that that's 3 to the 4/4 times 3 to the 1/4. Why would I do that? What's 3 to the 4/4? So it's 3x, and then what's stuck in jail is with the fourth root of 3. Holy cow. Right? That's how Mrs. Fasola would do this, going back and forth with the fractional exponents and not. Because 3 to the 5/4, that means there's a 3 that can be broken out. As far as being simplified there. So that is a wild one. That was a wild ride. Really cool. I'm glad I caught that I made a mistake on that one. Nice, Jad. Kind of a tough one. Cecilia. Oh, remember I told you this is going to get ugly with these rationalization questions? All right. So, Cecilia, can we reduce any of these? The 7 and 16 reduce at all? Ah, but what's the answer to that? Yes or no? Does 7 and 16 reduce? Nah, and there's nothing net root, so just get that over with. Hey, what's 16? How many, what times what time, what's 16? Break it down. Ooh. It is 2 to the 4th. Darn. You wish it was 2 to the what? No, 5th, right? So 2 to the 4th, so it's 2, 2, 2, 2. And then what about x to the 3rd? Is that enough? Yes or no? Okay, what do you wish it was? So make your dreams come true. What are you going to multiply both top and bottom by? 5th root of, how many 2's do you need? So how many more do you need? And then how many more x's do you need? That's what you do. Now, again, what did you accomplish? That annoying math rule. No radical in the denominator. Okay? So that's what we do. We make sure how many do we need and we make it happen. All right? I don't know how else I could say that. And then the whole point of you doing this, when you multiply these two, what's the 5th root of 2 to the 5th? Tell me what it is, Cecilia. What's the 5th root of 2 to the 5th now? 5th root of 2 to the 5th is, I'm writing it, 5th root of x to the 5th is, and that's what the denominator is now. The numerator, nothing will come out. It's a 5th root. It's ginormous. So it's the 5th root of 2 times 7, which is 14. 5th root of x squared, x squared. And no, nothing cancels. One stuck in the 5th root. So that is the final answer. You probably didn't feel like you accomplished much, but you dealt with that annoying no longer having a radical in the denominator. All right, all right, all right. So now we got a thing that's about like radicals. So what are like radicals? Equal radicands and equal indexes. So that's what a like radical is. Equal radicand and equal indexes, because now what we're going to have is an expression with multiple radicals, and we got to know how to simplify that scenario. So let's put an example of this, like, and this is kind of confusing for some students, 3 root 2 plus 4 root 2. Notice that the radicand is 2 and the index is square roots. So these are like radicals. And then who am I on right now? Miranda. Miranda, tell me the answer to this. What's 3x plus 4x? Just tell me what that answer would be. So what do you think 3 root 2 plus 4 root 2 would equal? You are correct. They work just like variables, where the radical is like the x parts. A lot of people try to do something with that root 2 when they add like terms. No, you don't do anything with the x. I mean, 3x plus 4x is 7x. So 3 root 2 plus 4 root 2 is 7 root 2. And just knowing how they add together is the key. So here's some other like radicals, like cube root of 2xy. That is the same as 4 cube root of 2xy. Those would be like radicals that I would be able to add or subtract. And the way they would add or subtract is just like how Miranda added that top one. This would actually equal 5 cube root of 2xy because this just works like a variable. All right, definitely like radicals. And then, of course, if the radicands are not the same, root 2 plus root 5, these cannot add. Do not make that root 7. You are making up a situation. And then another not like radicals, square root of 2xy cannot be added to the cube root of 2xy. The indexes are not the same, so these would not be able to be combined. So they have to be exactly spot on what the index and the radicands are. So 2 examples of not like radicals there. Okay, so here we go. And I just had Miranda go. So Evan, we know about the square root of 20 as you start writing this down, Evan. I like something better. What else is 20? What times what? So we can identify the perfect square. I want that. What's the square root of 4? Good. And that's how I want you to be breaking these down. I think this is the best way. How about the cube root of 16, Evan? We'll have you do 2 parts and I'll move on to somebody else. What's 16? I do want that because which one's a perfect cube? 2 or 8? Good. What's the cube root of 8? See, again, this is what we should be able to be doing fast. All right, I'll move on to Ryan. What about 250? What is 250? I got something better. 2 times what? 2 times what? Why do I want that? What's the cube root of 125? See, that's more efficient. And then knowing our perfect cubes, we can get that done. And then how about that? And then 2 stuck in jail. How about that root 5? Anything, Ryan? Okay, then Ryan, what are our like terms? Looking at this situation now. And what does that become? Be careful. I'll tell you what my last hour student said. What's 2 root 5 minus 1 root 5? Nice. It's 1 root 5. Last hour student, not to pick on him, he said 2. So I said, wait a minute. What's 2x minus x? Is that 2? And the answer is no, that is 1x. So 2 root 5 minus 1 root 5 is 2 minus 1, 1 root 5. Okay, so it works just like variables as well. So very good. And then how about the middle terms? And then yep, go ahead. Yep, you are correct. Circle it up and be done. Okay, so perfect. All right, so you get the idea behind those, I hope. And then we can move on. Okay, doing well, doing well, doing well. Hi-yo! I don't think I did this one. Let's see. It doesn't really matter. I think I have time to do so. So, Lauren, holy jeez. What do you think 2,000 is? Big number, eh? And I would stop there because do you know what the cube root of 1,000 is? It is. So cube root, see how there's 3 zeros? We could play a game here. The square roots of 100, 2 zeros. Cube root of 1,000, 3 zeros. Fourth root of 10,000, 4 zeros. This is a special division, of 10. This all works out because 10 times 10 times 10 times 10 is a 1 with 4 zeros, 10,000. So this, I just thought I'd break this down for you because that seemed kind of a little bit tough at first. All right, but you got it. So really good. So this becomes 10 times the cube root of 2. Square root of 2, nothing. What about 128, Lauren? And we're going to stop there because what's the cube root of 64? Oh, we do that. 4. You did square root by just kind of reactionary kind of situation. And then the 2's stuck in the inside. And then let's move on. Adrian Krozel, any like terms? Ten, yes. And what else? Which becomes, you got it? Did you say 6? Okay, I thought so. It just kind of cut out. And then square root of 2, wrong index. So we can't be combining those. All right, so we just leave it alone. Sebastian, you okay? It looks like you're all chilled out there. Okay, Sebastian, what about 20? And then what does that become then? Or what do I write? Oh, okay, nope. There we go. All right. And then what about 600? Oh, you're making that tough. I think 6 times what? What's the square root of 100? 6 is 2 times 3, so nothing in there. What about 125? Since it's a square root. What does this become? Like terms, any? And we could write that first. I don't know who you'd write first and who you'd write second. It doesn't really matter, I think. No rules behind that. So perfect. All right, I think we're doing some good stuff here. Okay, and now we're down to the multiplying. Oh, what a pain in the behind this is. So Carolina. Um, I'll do a couple of these because of time. I think we have 10 minutes left here. What word, Carolina, would you describe you might want to do with that root, cube root of 7, I mean? Starts with a D. You're right. Okay, and then the first one, not a whole heck of a lot happens. 2 times the cube root of 7, kind of like if you were multiplied by x, you just put it out in front, nothing occurs. But cube root of 49, by the way, what is 49? Carolina, what times what? And then we get multiplied by another through distribution, cube root of 7. Could you tell me what this becomes, Carolina? When we throw this all together in our head? Free 7. You're right. So we're done. 2 times the cube root of 7, nothing happened here, but something definitely happened here that actually simplified after we distributed that. You're done. You successfully, did that. Yes, is what we can say there. Excuse me. All right, do a couple more here. John, what word starting with F have I said probably a billion times since August? Oh, no, but good factors are good whats? Foilers. What's 2x times 2x? Huh? 4x, what? I didn't hear that last part. Right. And then what does this become? Ooh, little fumbled line there. And you forgot a negative. So how would you write that? I guess I could write it as 2 root 3x. I feel like I kind of want to do that, like keeping the number with the radical together. Okay, and then what about this? Inner? You're right. And then, ooh, let's get this one. First of all, what's a negative times a negative? What's root 3 times root 3? Nope. Root 3 times root 3 is at least root 9, which is what? It's a free 3. Okay, and that's what we want to be able to do on that one. Any like terms here? What does that become? Yeah, when you add those two. You're right. Don't mean to cut you off there. Yeah, you could say -4 root 3x. Yep, you're right. So nothing happens with the root 3 or the x, but the -2 and the -2 get added together. All right. So this is kind of an ugly one. Just do the operation and make sure you know how to work with the radicals. So that does end up working out pretty good. We won't do that one, but we will do this one. This is a little different. Um, who do we have now? Oh, Alessandra. What's the F word? Come on, good factors are good. Fo- well, okay, you like to distribute. You don't like to say the FOIL word, I guess. What's x times x? What's this become? And we usually write the numbers in front, but oh, there goes the pen again. And what about this one? Be careful. And then what is negative root 10 times positive root 10? And it's negative. What is the square root of 100? So we should write it as a free 10 and maybe help ourselves out. Hey, what happens to your middle term, Alessandra? This is called a conjugate when this is x minus root 10 and then this is x plus root 10. So notice the middle term falls out. We actually end up with a nice little binomial there with no radicals anymore. You okay over there, Ethan? Oh, cat. Okay, big yawn there. Sound my voice is mesmerizing for him. Actually, the opposite. Oh no! And then here's where I ended with the other hour. So who are we on here? Emily Ann Noyce. Emily Ann, what is the problem with this? There's a what? Where? Yeah, so this is rationalized, man. So I want to get to this one before we run out of time. When you have a binomial in the denominator, and that's what we could kind of count this as 2 plus root 5. Oh man, what do you do on this in order to rationalize? I'll show you the wrong thing. Some people might say, well, root 5. If I multiply this by root 5, then this becomes root 25 and I'm good to go. And you're not, because this would have to be distributed, and all you did was shift the roots over to here, and now we have 2 root 5 plus 5 down in the bottom. So you still have a radical in the denominator. So that doesn't do anything for you. So I did kind of want to show that to you. I hope I am taping still. I think I am. So I just have to just come out of left field. Can everyone say the word conjugate? Let me see your lips move. Conjugate. Good, Peyton. You were the best. Conjugate. I think I'm spelling it wrong. Oh, this is terrible. This is on conjugate. Yeah, there we go. I got to multiply by the conjugate of 2 plus root 5, which is 2 minus root 5. Now, Emily Ann and everyone else, I have to multiply both top and bottom because I have to multiply by a fraction that equals 1. just like those other fractional questions that we did. I'll find it. I'll find it. Oh, what the heck is that? I skipped that one. Will I find it? I don't know. Oh, here we go. See the green when we did that example? I multiply both top and bottom by the same thing. That makes it equal to 1. Let's try to find. See that? Oh, I didn't color that in green. I multiply both top and bottom by the same thing so that I multiply by a form of 1. But the problem with Emily Ann's here is we have a binomial. We get a big mess here. I'll get there. Here? No. Coming back? Yeah. All right, good. Stunning. So why the conjugate? Well, let's take the bottom here, Emily Ann. What's 2 times 2? And by the way, we can do whatever we want as long as we multiply top and bottom. So we have freedom. What's 2 times negative root 5? And then what's root 5 times 2? You see what's going to happen with that middle term? And then what's root 5 times negative root 5? And it's negative. So make sure you don't lose that. Up on the top, just distribute, but 1 times anything is just this thing. And then you already said it. And then what did you accomplish? You got rid of the radical in the denominator. But we ain't going to take that answer. We have to distribute that division and write this like this. And that's a much cleaner answer at the end. Okay, so multiplying by the conjugate. Yeah, I know that came out of left field. That's going to be the hardest ones. The hardest ones are dealing with the fractions. And the ones that we did previous, all of you answered it correctly, but I do understand how it is kind of hard to figure that out and the reason why. But first of all, you should see that that answer looks a lot nicer than the original, and there is no radical in the denominator anymore. So okay, I think we can call it quits on that. We did a whole bunch of different radical stuff, different types of questions there. So yet again, the calendar exists. I get these people. Oh, you guys are driving me nuts. How do I keep up with class if I've been absent? It's all right here. All right, everything. So that's what we can do tomorrow. I don't think I have any other stuff for you to do on the off day. Do the book work and do it appropriately. Don't be copying answers. That's why you fail if you do that. So, all right, we'll leave you be. Bye bye. I'll stop the video if I can. I don't even know if I can. There it is.